Okay, so for part 3 here of the pre-Unit 4 notes, we're going to go back to the questions from Unit 3, the AP questions that we saw. And in particular, I'm going to look at parts B and D. So we had the skier problem, there was air resistance, and for part B, they ask you to write a differential equation that can be used to solve for the velocity of the skier as a function of time. So a couple key things. One, when they give you that term, write a differential equation, they're asking you to write an equation that represents the derivative of a function, right? Or can be used to find the derivative of a function. But what this really means is, if we think about velocity, what is the derivative of the velocity? Well, the derivative of velocity we know is the acceleration, right? If you think of your velocity versus time graphs, right? The velocity versus time graphs, the slope of the velocity versus time graph is your acceleration, meaning the derivative, again, is the acceleration. So when they ask me to write a differential equation that can be used to solve for my velocity, they're really asking me to set up an equation for the acceleration. Right? So to do that isn't anything you guys can't do. The way that I would approach this is as a function of time, so as any function of time, we'll just think about my net force. Right? What forces are contributing to my net force? Well, at this point, if he's going down the ski, right, the skier's going down the slope, we know that the only force going down the slope would be the sine component of gravity, and then the only force working up the slope against him would be the resistive force of that negative BV, which I can plug in. So as I start to plug this in, I get my net force, which would be mass times acceleration, equals mass times gravity times sine theta minus BV. Right? So that's the expression that I've got here. So then, how does this relate to velocity and time? Well, the key is, what is the acceleration really? And again, the acceleration is really just the derivative of our velocity with respect to time. So I'm going to substitute A out of the equation and pull in dv dt. So I've got mass times dv dt equal to mass times gravity times sine theta minus bv. So write the differential equation that can be used to solve for the velocity. This right here would be that equation. Now if I wanted to go ahead and solve for m, that probably would be a good idea. Or solve for, dv dt, so divide by m, probably a good idea to do that. So I end up with dv dt equals mg sine theta minus bv all over my m. Okay, so again, what this means, this is my differential equation representing the velocity. What this is really saying is the derivative of the velocity, which is the acceleration, equals this whole mess over here. Right? So when they ask you to write a differential equation, they want you to write the equation that represents the derivative of a function. Usually for us, that's going to be relating to the acceleration or to the velocity function in some way, shape, or form. So in this case, it was using the acceleration and then realizing the acceleration is really just dv dt. Okay, so notice for part B they say set it up, but we do not actually have to solve it. They just say that can be used to solve for that velocity as a function of time. So this is actually my answer for part B, and you probably could have stopped here and that would have been perfectly fine too. But either one of those are my answer for part B. Okay, so part D here is the very, very important part. This is where it gets very tricky, and it definitely takes some practice to get there. So you'll notice I gave you homework that is built just around practicing this. It is very, very important you take that serious. Give it your best go, but if you do have questions over it, come find me so I can help get you some extra practice. Because again, this is a very, very important, one of the biggest new things that we will see throughout the course of this year, and it is a common one to make sure you're comfortable solving. But anyway, solve the differential equation in part B, which I rewrote down here, to determine the velocity of the skier as a function of time. So what I'm trying to do then is velocity in terms of time, right, equals whatever it may be. So I want my velocity function in terms of t. Well, in order to do that, because this is the derivative function right now, I'm going to have to integrate both sides, right? I'm going to have to find the integral. But before I can integrate both sides, there are a couple things I need to make sure I do. The first is I need to separate dv and dt, because I want to integrate one side with respect to the velocity so that it gives me my velocity function, and I want to integrate the other side with respect to time so that it ends up having something in terms of t. So the first thing I'm going to do, and it's a relatively easy step here, but just multiply both sides by dt. These are separate values, so I can just multiply both sides by dt, and obviously that cancels the dt out on the left hand side, And then on the right hand side I have this whole mess, mg sine theta minus bv all times dt. The other thing that I have to do, and it's very tricky for this particular problem, but the other thing that I have to do is I have to get any variables of v on the left hand side and any variables of t on the right hand side. Because I'm integrating this function with respect to v, I've got to get the velocity over here, and because I'm integrating this with respect to t, if there were any t variables, I'd have to get them on the right hand side of the equation. Now I actually don't have t in this, so I don't have to worry about moving that, but I do need to get the velocity, so I need to get this v to the left hand side. Well, this one's tricky because if you were to try to just get v over there, you'd have to do all sorts of, you'd have to add the v over, try to divide by certain things. It ends up being a mess. The easiest way to do it is just divide both sides by this entire function right here. So I end up with dividing by the entire mg sine theta divided, or minus bv. So I'm dividing both sides by that whole expression. Now be careful when we do this. I cannot cancel the m's out because this term does not have a m over here. Right? So right now I have m dv all over mg sine theta minus bv, and then that equals, on the other side it would just be dt, right? Well, the last thing I'm going to do, and this just simplifies it a little bit for me, I'm actually going to divide both sides by the m, so I'm going to go ahead and get rid of this term and just divide it to both sides, so that would make this 1 over m dt. Do you have to do that? You absolutely do not. Again, you would either do that now or do it later. I'm going to go ahead and just do it now to simplify it a little bit more for me. So at this point, I've got dv over this entire expression equals 1 over m dt. The biggest thing to recognize once we get down to here is we need to realize that I need to integrate both sides. So I'm going to integrate the left hand side with respect to v, because that's what the dv means, and I'm going to integrate the right hand side with respect to dt. Now at first it looks like it's going to be pretty bad. The important thing though is m and 1 on the right hand side are both just constants. So I could actually pull those out front if I wanted to. So I'm really just integrating. I pulled the 1m out front. I would just have 1 dt. Well, when I integrate this, right, if you were to integrate 1, the integral of 1 ends up being just t to the first power. Because think of this as 1t to the 0th power. I add 1 to that power, divide by 1. So when I integrate this, I actually end up with 1 over m times t. Again, the dt goes away. But I do have my plus c. So to simplify that a little bit, I have t over m plus c. So the right hand side of this equation actually not too bad, right? Nothing too tricky there. Now the left hand side at first looks like it's going to be pretty bad, until I remember both u substitution and I start to realize that mg, theta, and b are all constants, right? The only variable that I have on the left hand side is v. And so it's going to tie right back to what we've been doing with u substitution. I'm going to define the entire denominator as u, because then I'll just hopefully have something over u, right? So I get u equals mg sine theta minus bv. When I do the derivative of both sides, I do the derivative du equals, again, these are all constants, so that whole thing would just go away. But then when I do the derivative of negative b dv, well, I'm doing the derivative with respect to v because I'm trying to relate it to dv, right? So I do the derivative with respect to v, which ends up being negative b dv. The v becomes v to the 0th power. The b doesn't go away, however, right? Just the same way if I had 2x and I asked you to do the derivative of 2x, you would have 2, and then we've never actually used it, but dx is floating around. But anyway, so this is the relationship. So when I look at my integral, I have the integral of, I still have dv right now, all over u. Again, I can't integrate it yet because I have dv and I have u, but it's easy enough to make dv u, or du I should say. I just need to multiply it by a negative b. So if I want a negative b on the top inside, then I need a 1 over negative b outside, right? So I've got 1 over negative b, or negative 1 over b, and then I've got the integral of this whole thing, which would be du over u. Well, this goes to the last integrals we were looking at in the previous calc, right? The integral of du over u is just ln of u. So I have negative 1 over b, ln of u, and then plus another constant for this. Okay, so this point I've got the left hand side looks something like that. I've got the right hand side looks something like this. Now those are different constants. You'll see that the constants, we actually do a little bit of a trick with those to simplify it for us. Okay, but hopefully pause here for a second if you need to, look this over, make sure this makes sense. But this is where we're at this stage. We still have a little ways left to go though. So anyway, at this point, hopefully you're feeling confident with what we've done so far. There is one more trick that I'm going to show you, and it involves the constants. Those are both just constant numbers, right? So I could get C1 and C2 on the same side. I could obviously subtract C2 over, and I could just say that's some new constant as well, right? Well, better yet, I'm actually going to define this as ln of some constant, right? I'm going to say that the ln of some constant value equals whatever the difference between those two is. Again, these are all just numbers, so I guarantee no matter what two numbers these are, there's some third-party number that I could find that the ln of that function actually equals c. The reason I want to do that, I still have my negative 1 over b, I still have my ln of u, which in a moment I'll replace u here with what I have defined it for. But I'm going to combine these two together, and I'm going to represent those as ln of c. Right? I'm going to combine those two together and say that they're just some single constant as an ln function. So then that leaves me on the right hand side, which is this. The reason I want to do that is that allows me to take advantage of my ln properties. My ln properties say that if I have ln of a function plus ln of a function, it's really the same as ln of some constant, whatever that constant is, times my u. I just reordered those for no particular reason, but I'm just taking u times c. So if it would be easier to do that as ln of u times c, I'm just bringing these two together and inside that ln function. I still have my negative 1 over b out front, and I still have it equal to t over m. The reason I do that, almost there, but a few more tricks, right? I'm going to go ahead and solve to get the ln by itself. So to get the ln by itself, I'm going to multiply both sides by negative b over 1. So I have the ln of uc, or cu, equals negative bt over m. And then because I want to actually solve this, right, so again, I'll substitute my u back in just a moment, but to get rid of the ln function, I'm going to exponentiate both sides with the base of e, right? So I'm going to take both sides as the base e because that undoes my ln function. So now I have u times some constant equals e to the negative bt all over m, right? So I've got this expression, and then my last step here to isolate u is I'm going to divide both sides by that constant, right? So dividing by that constant, which really is just a new constant. So this is like our fifth different constant, but ultimately I end up with u equals some new constant times e to the negative bt over m. Now, sometimes it is helpful to just remember that it's going to end up being that constant times whatever, but I do want you to be kind of comfortable getting there as well. So anyway, almost there. They want me to solve for my actual velocity function, so I do need to go back and plug in whatever I've defined as u. So this whole thing I defined as u, right? So my mg sine theta minus bv, I'm going to plug that back in for u. So again, resuming here with mg sine theta minus bv equals c times e to the negative bt over m. Right? So there's a couple more steps that I need to do. One is I need to isolate to get v by itself because they want me to solve for my velocity function. The other thing that I do need to do here is I need to solve and figure out what c actually is. Right? C is a constant, but they give me enough information to find it. Right? So in order to find that, I have to go all the way back to the original context and start thinking about the equation. So if you go back to the original question, they say that the skier starts at rest from time t equals 0. So the initial velocity is 0, the time is 0 as well. Well, that helps me find c, because I know that the velocity is 0 when the time equals 0. So to find c, if I plug that in, well, I would get mg sine theta minus b times 0, so that would go away, and then equals c times e to this whole power would become 0. And anything to the 0th power is just 1. So this whole e to the 0th would just become a 1. So that tells me c then equals mg sine theta. So I have mg sine theta minus bv equals mg sine theta times my exponential function. I'm plugging in for e here, mg sine theta, times e, and then to the negative bt over m. Now you still have to solve to get v by itself, but I will trust that you guys can do that on your own.